Hello everyone, welcome back. This time we are going to design an underground reinforced concrete tank. In this design of this tank, we will also cover the shrinkage and temperature stresses that are given by IS 3370 Part 2, which are also called as immature crack widths. So let's see what all tools we require for this design. Tools means I would say number one is the IS codes, number two is the books that we are referring to, and number three are the computational tools that we require. So let's start with the IS codes. The first IS code that I would recommend is number one is IS 3370 Part 2 2009. This has been revised in 2021, but we are not referring to that because we are going for WSM design, working stress design. We will do working stress design. And in this code, we are given, we will take permissible stresses. Number two, this code will give is this also gives crack width, the limiting crack width, which is permissible. This will also give us the minimum reinforcement. Okay, another few things are also there that are there, but this code is mainly for the RC tanks, reinforced concrete tanks. And number two, second code that we will refer is IS 456, which is important. IS 456 we will use the durability requirement criteria, like to what site your tank is located, and which minimum concrete grade you should use, and what is the like minimum concrete cover that you should give in your structure, right? Number three is, so you can see right here, and this is the concrete covers and concrete strength. Okay. Third one is IS. Also along this, we will use SP16, which is a like another tool for obtaining reinforcements as per IS 456. So table 71 we will use of this IS this SP16. Okay, this you should remember. Now we have IS 3370. Third recommendation is IS 330 Part 4 1967. This code is revised in 2021, but it is kept as it is. So, what is there in this IS 4 no, 370 Part 4? This code has design tables. This is a supporting code of IS 330 Part 1. Okay. These design tables have, see, this I will explain a little later. Just give me some time. Let me finish this series. So another thing that we should refer is number four. There is a book called Before going to the book, let's just complete this code. One more code is required. Kilo part 1, 209. This is part 1. Part 1 is for general idea of how tanks are designed in civil engineering in India. General requirement, and it gives you a good knowledge of tank design. What is the standard practice in India? There is a book as a fifth reference, Timoshenko. Don't worry, you don't need to read this book throughout. Just you go with table number 45. it is sufficient. You should know only table 45. It is sufficient for you to complete this design. Don't worry about this reading this book or for this course, in this design. Only table 45 is important. Okay. So these are the references that we will use. Also, there is a design tool which is Excel. We need Excel. Just to make sure you're doing right calculations, we start with using Excel. Okay, we will do design in Excel. So here I will show you the calculations, but we can implement these calculations in Excel. Okay, this is how we will start. Now, here we will not be explaining things in Excel, but these are easy to understand. You can refer Excel, and I have already referred Excel, but it is not presented here. Okay, and let's continue with how this IS 3370 part 4, this thing, this thing, this thing, how, what is given, what are these design tables. Let's see this thing first. Okay, so see, in a RC frame structure, what do we have? We have columns, beams. Okay, also these columns and beams we have. So when we are given some loading, suppose the type on the type of the building, say this is a library, then there is a load of books. If that is a public property, then there is a general live load that we take as increased factor. If there is a residential building, we take some standard loads. So some loads are there on the slab. These are the slabs. Okay, on this floor, this is the slab. So these slabs will take the loads, whichever load you assign to them. These slabs will distribute the loads to the beams. We have these surrounding beams. You see this? These are the beams that will take this load from the slab. These beams will transfer these loads to these columns, and then similarly this slab also will transfer the loads to the surrounding beams, and from beams it will come to the column, and from column to the foundation. And depending upon the properties of your soil, you will give the corresponding area of the footing, the type of the footing. So this is all we can design all by hand, provided that you know how to distribute the load from the slab to the beams. So this is the typical part. See this slab, you take the slab here. Suppose this is a one-way slab. I have already explained in this previous video. If length, this is B. If length upon B is greater than 2, this is a one-way slab. So the load is distributed like this. This half of the load of this slab is taken by this beam. Half of the load of this slab is taken by this beam. Okay. If it is a two-way slab, so what is the load distribution? See, two-way slab is like this. L upon B is less than 2. Okay. So load distribution is like this. And this load is distribution like this. This triangular load. You see this triangular load? This load is taken by this beam. This trapezoidal load is taken by this beam. Similarly, this trapezoidal load is taken by this beam, and this triangular load is taken by this beam. So this is a load distribution. If this is a rectangular slab, then we have yield line theory. This yield line theory gives like if you have a W load acting on this surface, then what is this triangle? How this triangular load will be converted to the UD along this beam. So from yield line theory, you transfer the load of the slab to the beams, right? And other way is you do the FE analysis. So these are two methods that through which you transfer the load of a slab to the beam. Now see this tank case. what happens in the tank? We have this tank. Okay, just draw a tank. Just let me see. This little vertical. And just we have this tank. So in this tank, this is the bed. We have these faces. Number one, two, three, four, and this five. And if there is a top slab, then six. Okay. All these faces are two-way slabs or one-way slabs, depending upon the case. So these slabs are connected directly to each other. There is no intermediate beam or column. There is no beam here. There is no beam here. There is no beam. There is no beam. No column here. These slabs are directly connected to each other. So there's a combined effect of all these slabs acting together. When there is a load acting on this face, so this face will bend like this, right? This at this end will try to pull this edge. You know, these things are there. This will also try to pull this thing, and also the boundary condition, like whether this edge is you have made it fixed or not. If it is a free, if it is a hinged edge, or it is a fixed edge. Similarly, this bottom value, whether you have made it hinged or you have made it fixed, these walls, how they are connected, they are boundary conditions. Like it depend upon your case, upon your tank, how you are going to design it. What are the site requirements of the user? So depending on those boundary conditions and shape and size of tank, some design tables are there. What do these design tables do? These design tables, they give the coefficients of see the coefficients of moments at different locations in a tank. What are these coefficients? These coefficients might when multiplied by a certain factor alpha. Alpha is a function of type of load intensity, water load, soil load, and shape and size of the tank. This is L. Sorry, this is H. This is H. This is L. This is B. Okay. So depending on the shape and size, in this loading, what kind of load you are taking? Is it a water load? Is it a soil load acting from outside? What kind of load it is? So this alpha is a factor which is constant. Okay, for a given table, this thing is constant. Only thing that changes is the coefficient. These coefficients are given at various nodes. See, what are the nodes? Just zoom it. See, this is the center of this stoppage. Center of this rectangular or rectangular face, bottom of this face, corner point, middle of the edge, bottom of the edge, this corner, this middle, this bottom. Similarly on the other face. Okay, this you can see. This is always there. Like the way you obtain these coefficients for this face, you can obtain this for this face also based on this ratio of this length and height, width and height. So this is how you the coefficients are given. Let me just show you briefly how this is acting. We have this IS 3370 part 4 is here. So this is the IS 3370 part 4, 1967. This is our boundary condition where we have bottom edge fixed, side faces also fixed, top is free. We are not going to fix the top side to the uh, wall to the tank. So we have this A is the height of the wall, this A is the height, B is the width of the wall, B by 2 and B by 2, so is the 3. W is the density of the liquid. W is the density of the liquid that is filled inside. So this is the triangular load distribution, which is also called as hydrostatic load. Horizontal moment can be calculated by multiplying My into Waq. This is not visible clearly, but this is Q. So My is here. These are My's. You see this? This is My. This is also My. This is also My. Vertical moment is mxwaq. Mx is this. This y is equal to this. There are coordinates you can see. This x is downward, y is here. So this is x is equal to 0 and y is equal to 0. And here y is equal to b by 2. Here x is equal to a. So you see this x by a. There are some values given 0, 1 by 4, 1 by 2, 3 by 4, 1. So these values are given at xy is equal to 0, xy is equal to 1 by 4, xy is equal to 1 by 2, xy is equal to 1 by 3 by 4, and xy is equal to 1. So these are the different points there for which the values have been given, and these values are given along the width of the plate or the face. So this width is governed by y is equal to 0 means center line, y is equal to b by 4 means this center line and edge, the midpoint of this. So here it is y equal to b by 4 and y is equal to b by 2 is the edge. So these values of horizontal and vertical moment are given in this IS 3370 part 4 1967. Similarly, this type of table is also given for Timoshenko. See, we have this Timoshenko. This is a theory of plates and shells, Timoshenko. I have this hard copy also. So, in this, what is there? See, this type of loading is Timoshenko has given coefficients for the hydrostatic load. See this hydrostatic load figure 101 and this uniform load, which is surcharge. We will also utilize this for surcharge loading. So these tables are given in Timoshenko also with some little difference in the coefficients calculation. But it is a similar pattern. You see this table 44, this is for the uniformly loaded rectangular plates with three edges built in and the fourth edge free, which is the uppercase. And this is table 45 from Timoshenko. Deflections, welding moments, and reactions of hydrostatically loaded rectangular plates. Hydrostatically means this pattern. Is a triangle. Water load is active. So this is called hydrostatic. This also applies for the soil load. Okay. So this Timoshenko and this IS 370 part 4 1967, both of these we will utilize in the design. Right. Now this is about the basics. Now we will, before starting the full-fledged design of an example, let's also see what are the basic concepts of a tank design. What are the how these loads act and what are the critical load combinations that we should consider in the design. Okay. So let's start this.